Welcome back. Let's talk about graphical analysis of recursive algorithms. So in the previous video, I just introduced the idea of recursion, and I looked at some classical recursive algorithms. And we did talk about the time complexity a little bit on that, but you may have noticed in the previous video that we need some better methodology to analyze recursive algorithms. So that's what I'm going to show you in this section. So this is a graphical method where we're going to follow these rules right here to draw a diagram. And then we're going to look at the shape of the resulting diagram, and that can help us determine the time complexity. Okay, so basically, here I'll go through these rules real quick. We're going to draw a box for each function instance. Okay, so every time there's a call to a recursive function, we draw a box. And then inside that box, we put more boxes for the local variables and the parameters. Okay, then we put values inside those little boxes that are, when arguments are passed to a function, we put those values in the local parameter boxes. And if there's any global variables, we'll show those outside of the function call boxes. And if the values change inside the boxes, we cross them out and write new values. It's good to duplicate all the code that's in a function in the function call box. That's good, although you can get away with showing less than all of the code sometimes, just for clarity, or for time constraint, but it's good to show all the code. And then you can put arrows inside showing where the code is flowing. You can put arrows between the function calls showing arguments being passed to functions and then return values coming back. And I'd like you to show the output. Okay, so the main reason we're doing this is so that we can use it as a tool to determine time complexity. But there's value in this methodology here just by itself, because let me look at it this way. You learn to write code. You type some code in, it runs. You think you know what's going on. What else can you do to deepen your understanding? Well, you can write more code. That's true, but sometimes it's good to do other things that help you think about code. It's kind of like a little bit like working out. Like if you're a basketball, if you like to play basketball or something, for example, you might want to do a little bit of weights, right? Just to work on your strength. Now, it's not exactly the skill that you need for basketball, but it helps. This is kind of what we're doing here. We're looking at a way to analyze the program flow in a function that is not just by writing code, right? You still need to write code, and the more code you write, the better. But if you have another way to look at program flow, we call it, if you have a graphical way to look at program flow, that helps you deepen your understanding of what's happening when you're actually writing code. Okay, so that's the point of this stuff. Okay, but for time complexity purposes, what we're going to do is we're going to draw these diagrams, and then we're going to look at the diagrams, and from that we can sometimes infer what the time complexity might be. For example, if the diagram looks kind of like this, where you have a bunch of boxes, each one of these boxes is a function call box, and the number of boxes is proportional to the problem size, n. That's going to be big O of n. Right? If you have something that looks like this, typically it'll look like a tree, where for a given problem size n, if you have 2 to the n boxes, then, well, that's 2 to the n time complexity. So in other words, in this example, I have a problem size of 3, and I happen to have it doubling every layer, so that works out to 7 boxes, or, well, technically it's 2 to the n minus 1, but we just round it to 2 to the n. That's essentially the same. For large n anyway, it's practically the same. Okay, that's another shape you'll get. Now, the third shape that comes up is something that it looks like the first. That is, it's a line of these function call boxes, but it's not proportional. And so you have to kind of execute the function several times for several different values of n, and then graph it. And if you, for this one here, I have, you know, different problem sizes, and it's all going to generate three boxes. Okay, then I have for a bunch more problems it generates. I guess that was 2 before then. For a bunch more problems, it generates 3. And then for a bunch more problems, even longer, it generates 4. So you're getting this kind of a discrete logarithm, we call this. So this is going to be log n. Once again, it looks like n, but the number of boxes is not proportional to n, the problem size n. It's logarithmically proportional to n. So these are the main shapes that you're going to get. Most of the algorithms we look at will have one of these 3 shapes. Now we're going to look at Queen's, which doesn't have any of these shapes. Okay, Queen's is kind of an outlier. It's a weird looking thing. All right, but we'll talk about that. Okay, so here, let's go through a couple of classic algorithms that we've already looked at. So I've got factorial here, and here's the code previous in the notes, back some pages. Here's the code for factorial, and we talked about that in a previous video, how that's big O of n. Now if you use this execution method I'm describing to you, this is what you get. So you call from main, you call factorial, so that's this box here. So there's a box for main because main is a function call, so you draw that box, and then there's the code that's in main. Okay, then you call factorial, so you draw this box for the first call into factorial, and then the 6 is what's passed. So this, well, this is for this, yeah, 3. It's a little, the code is a little bit different in these two examples. Here we're calling main for 3, or we're calling, misspoke there, we're calling factorial with 3. Okay, here I'm using 6, so it's a little different. Use the 3 here for this diagram. So a 3 is passed on this line and comes into this local variable n3. The parameter n is 3. This is a simplified version of factorial where we're just returning 1. There's only one base case. It still works. Anyway, so n is not 0, right? So the else branch goes, and the 3 is still here, but we call factorial with 2. So n minus 1 is 2. You know, 3 minus 1 is 2, so a 2 is the argument. And you should show these numbers on your execution. Here the return values are being shown, but not the argument values. Show them all. So the 2 comes down in here, and then we put that in this local box right here, right? And so n is not 0, so the 2 is staying there. And then in here we're calling fac with 2 minus 1, which is 1. So we're passing a 1 down into this box, right? So every time we call factorial, we draw a new box, and we put the new local variables in there, and then we put all the code. And I like to label the values that are in here, and then label the arguments. You know, 3, 2, 1 are the arguments that are being passed. And so we come in here, and the 1 hangs out, and then this is a 0. And so the 0 gets passed to another called a function, to fac. And n gets passed into this box right here. And let's see. So now n is 0, so it's going to return a 1. It's going to do the true branch, right? You could even draw an arrow there to make it explicitly clear which one of these guys is getting called. And the 1 comes back here. Okay, so the return value from this call is 1. Right? So we're doing 1 times 1, which is 1. That's this return value. So this is good because look, there's an expression here. We're doing n times factorial of n minus 1. There's an order of execution here, right? First, the stuff inside the parentheses gets executed. You have a 2, right? Then that 2 is passed, and it goes all the way, and it's going to come back, and then the return value will get multiplied times n. So just this is a way to study simple program flow. Like I was saying earlier, besides just writing code, you know, what other ways are there to look at program flow? Well, you can do a classical flow chart, which they teach you often in beginning programming classes. This is not exactly that, right? This is not a what's typically called a flow chart. It's similar to a flow chart, but not exactly. Okay, this is a kind of a graphical method for specifically for recursion, and it's flowchart-ish, but not exactly. Okay, just want to point that out. Don't start doing triangles or diamonds and circles and stuff that you see in traditional flowcharting. That's a different kind of method. It's not as useful for what we're trying to get done here. Okay, but anyway, back to this thing here. So the one here comes back. Then you multiply and you get a 1, and then that's the return value from this return statement right here, right? This is returning this 1, which comes back here. And so the return value of this call is 1, but now we do the multiplication, right? After this fact here returns, we do the multiplication, and we get a 2. And that's what is being returned here, is this 2, which comes back here. So the return value from this is 2. Then we're doing 3 times 2, right? So let me just say this again. First we passed in a 3. We did this n minus 1, which gives us a 2. That was passed over here. And it comes all the way down and all the way back, and a 2 just happens to be another 2. Comes back, and that is what the entire function call fac n minus 1 expression evaluates to. Right, so there's the stuff inside the parentheses, which is 2, and then there's the entire function itself, which happens to also be 2. So this is good stuff, you know, to help you keep just regular programming flow clear in your head. Anyway, then we do 3 times 2, which is 6, and that's the return value here back to main. So this thing will output a 6. There's the output. Okay, so what I just did was I sort of walked through all these steps right here about what to draw. Okay, now I just want you to do this for the homework. Let's look at a couple more of these. All right, let's look at efficient exponentiation, which I have the code for. Here's the code for efficient exponentiation, and here's what the diagram would look like. This is what the recursive hand execution diagram would look like. It's a little bit rough, but here it is. So let's look at the code real quick. So we've got 2 base cases, return 1, return x, and then we've got a if-else where we're going to do either this branch or this branch. I've only showed the code that's executing in these boxes, although for your homework, you should type all this stuff up, and then it's pretty easy to show all the code because you can just copy and paste and put it in there. But let's call, where's main? I don't have main in here, but let's say we called main with 2 and a 7 because we want to calculate 2 to the 7. So we're calling this function pow with x2 and n7. So we draw a box, you know, and I just labeled them P, but you could be more explicit, label them pow. So the 2 gets passed into x, and the n gets passed into 7. So draw these little boxes for the locals. The local variables, which are these 2 local variables, x and n, also happen to be parameters. So let's see. N is not 0. It's not 1, and it's odd. So this is the line of code right here. This line of code is the one that executes. So I've written that out. And it's pow x times x is the first argument, and n div 2 is the second argument, and then I multiply times x, and I put in the values of x, which are 2, 2, and 2, and I put in the value of n, which is 7. So what happens here? The 2 times 2 gets evaluated first, right? And that's, oh, I have 64 there. That should just be, 4. And 64 is the return value. This should be 4. And this guy, that's 3. 7 div 2 is 3. So those are the arguments to the function called pow. 4 and the 3. This is x. X is 4, and n is 3. So you put those in these boxes here. You draw another box for pow, and you put these 2 boxes for the locals, and you put the 4 that's passed in here, and you put the 3 that's passed in here. And once again, 3 is odd, so this line is the line that executes. So you write that line out again, and then 4 times 4 is 16, and 3 div 2 is 1. So those are the arguments that are passed to another instance of pow. Okay, now n is 1. Right, n is 1, so we just return x, which was 16. Okay, so 16 comes back on this return arrow right here. 16 comes back, and that's what the entire pow expression evaluates to, is 16. This entire pow paren is 16, because it evaluates to the return value, 16. Then you multiply times 4, right? Because this multiplication times 4 happens when we come back to pow, right? So now 16 times 4 is 64, and that's the return value, 64. I should write it on this line. Okay, so we're returning 64 back up to this instance of pow. And then the entire expression pow paren evaluates to 64. Okay, pow paren is 64. And then we do the multiplication times 2. So we get 128. Okay, and then this return statement returns 128. So that's what I written on this line right here, back to main. So 2 to the 7 is 128, so it works. Okay, this is the execution method. You draw a box for main, you draw a box for every time you call a function recursively. You show the locals, show the values that are in the expressions. You should show all the code in here. And then show the arguments being passed, 4 and 3, this 4 and this 3. Show them being passed. Show the return values coming back. And yeah. Okay. What's the time complexity of this thing? It's, well, for n equals 7, I got 3 boxes. 1, 2, 3. You would have to execute this several times. And if you did it for 8, what would happen to n? What would be the sequence? Like for 7, it was, let me draw some. For 7, the sequence was, it was 7, 7, then it was 3, then it was 1. So 7, 3, 1. That's 3 boxes. For 8, if we pass an 8 in here, it would be 8, and then we div 2, it would be 4, and then we div 2, it would be 2, then it'd be 1, it'd be 4 boxes. And for 9, it would be 9 div 2, which is 4, and then 2, and then 1, it'd also be 4 boxes. For 10, it'd be 10, then div 2 would be 5, then 2, then 1, also 4 boxes. 11 would be 5 to 1, and then it gets bigger. And for 12, it's 12, 6, 3, 12, 6, 3. That's still 4 boxes. Am I doing this right? 12 div 2, that's 3 boxes. There's 4 boxes. So what about 13? It's going to be, it's still going to be 6. It's going to be 4, right? When does it get bigger? I think it gets bigger at, what does 15 do? 15 is going to be 7, 3, 1. It's still 4 boxes. It gets bigger at 16. There's a bunch more 4s. Error, I should fix that. But at 16, it finally gets bigger because that's going to be 6, and then we're back to this 8 thing. So 8, 4, 2, 1. That's 5 boxes. And then 17, 18, 19. That's a bunch more 5s. Okay, so there's a bunch of, you know, between 8 and 15, there's a bunch of 4s. Then between 16 and 31, there's going to be 5 boxes. Okay, so this is a discrete log. All right, and that's where you get the log n. Okay, so you execute the hand execution diagramming technique, and then you have to be careful that it's not n. What did we just do before this? Was it Fibonacci, or was it? What did we do? We did factorial last time. That was the first one we did. And I didn't draw this table on here, but if I did, it would just be n on on both sides. The number of boxes here is proportional to n, right? If I did like here I called fact for 3 and I got 1, 2, 3. I got 4 boxes. This is the number of boxes. And if I would have done it for 4, I'd get 5 boxes. And if I would have done it for 5, I'd get 6 boxes. And 6 would be 7 boxes. And 7 would be 8 boxes. So it's off by 1, but it's still growing proportionally. So it's, it's roughly n on both sides. Forget the +1 thing. It doesn't matter, really. This is big O of n. Okay? But factorial is this thing, because the number of boxes is proportional to the problem size. The n, the 3 is the problem size. In this case, 3, 4, 5. Okay, but this problem size increases, the number of boxes increases proportionally. But that's not what's happening here with efficient exponentiation. Even though you're getting a sequence of boxes, that sequence of boxes grows slower than the problem size n does. Okay, let's look at another one. Let's look at Hanoi. Okay, I got the code from Hanoi, which is back up some pages in the notes. And let's see. So we're calling the problem size n is 2 here, and the start peg is the first peg, and the goal peg is 3, and the spare peg is 2. So the execution that we're doing here is it's this one. We're doing this this thing right here, where we're moving 2 pegs, or sorry, 2 donuts. N is 2. We're moving 2 donuts from peg 1 to peg 3, and our spare peg is peg 2. Start, spare, goal. That's the parameter order over here. Number of donuts. What's your start peg? What's your goal peg? What's your spare peg? So we're doing 2. We're moving them from starting peg 1 to goal peg 3 with spare peg 2. So that's shown with our diagramming method. So we have our box for main. N is 2, starting peg of 1, goal peg of 3, spare peg of 2. It's passed into an instance of Hanoi. The n goes into this box too. The start value of 1 goes into here. The goal goes into this G box 3, and the spare goes into SP box 2. N is not 1, so we do this else branch. And the else branch consists of 2 calls to Hanoi. So the first call is this H call right here, and the second call is this other H call here. So this first H call, we're passing N minus 1, which is 2 minus 1, which is a 1. We're passing it over here to this second call to Hanoi. And then we're passing the next 3 parameters, the start, the spare, and the goal. We're passing them in a different order. Okay, because now the order for Hanoi, the parameter order is start, goal, spare, but we're mixing it up. We're passing instead of 1, 3, 2, we're passing 1, 2, 3. So what was the spare here becomes the goal here. All right, it's just about impossible to visualize this at a higher level, but what we want to do here is just follow the code. Okay, do what the code says. So see, it's in the call to Hanoi, start, goal, spare. In the parameters, that is. In the parameters, that's the order, start, goal, spare. But on this call, these guys are swapped, right? Now it's start, spare, goal. So the 3 and the 2 get swapped to a 2 and the 3. Just do that. Just follow what the code says. So the 2 and the 3, they still go into the boxes in the same order when it comes back into Hanoi here, you see. So it's still the parameter order here, or the argument order. The argument order is 1, 1, 2, 3. So that's the way they go into these boxes, 1, 1, 2, 3. Okay? Then N is 1 here, so this does the base case where it just does the C out. Then it comes back. This call to Hanoi comes back after coming in and just doing the, I think I was pointing at the wrong thing. It comes in here and then does the C out and then comes back. Leaves this guy. Comes back to the first call, which was back in here. And then this guy does the C out. Then it does a second call to Hanoi, which comes down here, passes this program order 1, 2, or this argument order 1, 2, 3, 1, comes into these parameters 1, 2, 3, 1. And here N is 1, so we just do a C out and return back to this guy where we started from, which was here, right? So then this guy returns finally back to main. So once through at a higher level, we come in main, we come into Hanoi. It calls Hanoi. Come into Hanoi. This Hanoi does a C out and returns back to the first Hanoi, which does a C out and then calls Hanoi again. Comes into this guy, which is another instance, another brand new instance of Hanoi, which does a C out and then returns back to the first instance of Hanoi, which was back to here. And then this guy leaves. That's the program flow. So you get these 3 C outs. You know, this is the first one that gets the first C out does this line of text, and comes back to this Hanoi, which does this C out. You get the middle line of text, and it calls this third Hanoi, which does a C out right away, and you get this third line of text. Okay, then all you got to do is find a human to do these things. So this is the technique, all right? You just take this code and you draw boxes for every function call. You list the parameter, in little boxes, and then you execute it, passing arguments and putting them in the right boxes, and then put all the code in here, and then draw some, when you get a function call, draw another box and list the parameters, and just do what the code says. Just do it. So this will help you just follow code in your brain and train your brain to solidify what simple program flow is. Okay, because you can code, we can all code, right? We've all had a beginning programming course. We can get our code to write, you know, when we're lucky. Some days better than others, right? But the only way, the ways to get better, one way to get better is to write code. Another way to get better is to study code by representing code in a different way. And that's what we're doing here. Okay, so we end up with these diagrams. And then what's the time complexity? Well, n was 2 here. N was 2, and I have 3 Hanoi boxes. So that's what this chart is showing here. For n was 2, I have 3 boxes. If I called in Maine again, if I called Hanoi from Maine with 3 donuts, right? 3 donuts, I would get 7 boxes. Okay, this one would double. This call would have 2 more boxes, and this call would have 2 more boxes. I'd get 7 boxes. And if I did it with 4 donuts, I'd get 15 boxes. And each box represents a certain amount of work, right? That's why we count the boxes, because we're trying to get some measure of the work done. Anyway, you generate a table like this, and you can see that it has a 2 to the n shape to it. All right, let's look at another one. Let's look at n queens. Actually, here's n queens. So the recursive function we're interested in is this build thing. Build has a loop in it, and it's going to look something like this. So you've got main. You call build. I'm just going to use a b, and let's say we pass value 1 in it. This is this guy goes over here to build, right? N comes in here, and then there's a loop that goes well, it goes 8 times, and we're calling build in this loop. Okay, so it's going to go over here and do some stuff and come back, and that could happen up to 8 times maximum. It doesn't always call build because there's an if in here. If something, then do build. Okay, but it could do this up to 8 times. This thing would be 8 times. We could end up with a maximum of 8 builds, right? 8. So it's gonna call it from what's the parameter that's being passed? N. Every time it calls it, it's getting the same n, but the same n is getting passed. But it could go. That could happen 8 times because it's doing it for different rows. You have to look at the code, and then each one of these could be a maximum of 8. Okay, and like that. This is a very rough, just a high level kind of a thing. But you have the first call to build that results into 8 calls. Ooh, sorry, you couldn't see that. But you have the first call to build results in up to 8 calls max. Then each one of those results in up to 8 calls max. So you can see this grows like crazy fast. So I am gonna ask you to execute this, but not for 8, just for 4, right? Just for 4. So to help you, I have plus a semi solution. Okay, I think I'll do one more video on how to do the homework, but we've kind of talked a little bit about how to do the homework here. But I think I'll talk a little bit more about that. All right, great. See you next time.